This is section 6.1. In this section, we're going to be speaking about solutions to higher order differential equations. So this is the theorem that we are going to be applying in this section. It's called the existence and uniqueness theorem. So suppose that rho 1 through rho n, this little p looking Greek symbol is called rho. Rho 1 of x through rho n of x and g of x are each continuous on an interval from a to b that contains the point x naught. Then for any choice of the initial values, these little gammas, don't let all the Greek letters throw you off, gamma naught, gamma 1, all the way up to gamma n minus 1, there exists a unique solution y of x on the whole interval from a to b to the following initial problem. So let's try to break this down and understand it in simpler terms. Suppose that you have this differential equation. Now, up to this point, we've really only been dealing with things that go up to like order 2 mostly. So this is going up to order n. So that's what's unique about this section, is this is a way to find solutions all the way up to order n. So we have the nth derivative of y plus some function of x times the n minus 1th derivative plus, and then all the way down to some function of x times the original function y. And then you can also have some other function x here on the right side. So this is just a general form for a differential equation in this linear ordering for an nth order. And now this is what we would call an initial value problem, because we are given the initial values for y, y prime, all the way up to y to the n minus 1, or sorry, y to the n minus 1th derivative. Now, as long as these are all taken at the same value, typically when we do these types of questions, it's centered at 0. But here, as long as it's centered at any x naught value, what this theorem is saying is that there is a unique solution for y on some interval containing x naught. So now we're going to look at some of the questions in the textbook using our existence and uniqueness theorem. So question 2 in the textbook says, determine the largest interval a to b for which our theorem guarantees the existence of a unique solution on a to b to the initial value problem stated here. Y triple prime minus the square root of x times y is equal to sine of x, where our initial values provided are y of pi equals 0, y prime of pi equals 11, and y double prime of pi equals 3. So what the question asks, not for the solution, but what the largest interval on which such a solution may occur based on our existence and uniqueness theorem. So we want to find some values of x on this number line where this will hold true. Now, let's look at what the theorem says. The interval must contain the point x naught. So here, that point is pi. Pi is the value we're plugging in for all these initial values. So we've got pi here, and we just want to know how big the interval is that can be guaranteed by our theorem. So what it says is, suppose that rho 1 through rho sub n and g of x are each continuous on the interval a to b. And that's really the only statement that's necessary. We just want to find the interval on which all of these functions are continuous. Now let's check what these functions are. We have negative square root x, and we have sine x. Now for all x, positive, negative, rational, irrational, sine of x is actually a continuous function. You know, using that old method, you can draw it without ever lifting your pen. Negative square root x, not exactly. You can't take the square root of a negative number. So 0 is going to be at the lower end here, but at the upper end, it's just going to be infinity. So as it says here, we are looking for an interval that contains x equals pi, and both negative square root x and sine x must be continuous. So the largest solution is from 0 to infinity. Now, I've put a square bracket here around the 0. But if we are going to follow the existence and uniqueness theorem to the letter, it puts a round bracket on both sides. Okay, question 4. Same thing, we've just been given a different problem. And now there is an important first step here. There is a coefficient in front of the leading term, y triple prime. In our theorem, the highest order derivative does not have a coefficient other than the trivial coefficient 1. So we must divide through by this coefficient x times x plus 1. So we're going to divide the entire function, the entire equation, by x times x plus 1. So now we must find a largest interval that contains -1/2. That's the value that we plugged in. That's our x naught value. Such that -3x over x times x plus 1 and 1 over x times x plus 1 are continuous. So it must contain -1/2. Now, this 1 over x business, that will cause a problem at 0. That's when that function will stop being continuous. And 1 over x plus 1, well, that stops being continuous at -1. So the largest interval that we could draw that contains the -1/2 goes all the way from -1 to 0. And that's what we have as a solution. Okay, question 8. This is where we're going to move on to linearly independent and linearly dependent stuff. So something in differential equations that we didn't get to in this course, but you may in the future, is the idea of the Wronskian. We introduced it a little bit, but we're not actually going to go into any questions about it. The Wronskian allows you to do a lot of things with differential equations, but what's important is determining whether the equations you're dealing with are linearly independent or linearly dependent, the functions you're dealing with. So we are just going to do a little quick example on linearly independent versus linearly dependent, so that in your future courses, you'll have a better understanding of this Wronskian. So we want to know if y equals x squared, y equals x squared minus 1, and y equals 5. We want to know if that's a linearly independent set or a linearly dependent set. Now, the way to determine this is you add them all together multiplied by scalars. So a1 times x squared plus a2 times x squared minus 1 plus a3 times 5 equals 0. Now, the definition of linearly independent is that all three of these scalars must equal 0. a1 has to equal 0, a2 has to equal 0, and a3 has to equal 0. If we can reach that this is true, then we have proven linearly independent. However, if we can show that any of them are not equal to 0, even if it's just a1 equals 0, a2 equals 0, and a3 equals 4, whatever, if we can prove that this statement is true, if any or all of them are not equal to 0, then we have proven that the set is linearly dependent. So let's see what we can do here. Let's multiply through. So we have a1 plus a2 times x squared plus 5a3 minus a2. We'll shift this to the other side, subtracting from both sides, and then we'll divide by a1 plus a2. So we now have that x squared is equal to negative 5a3 minus a2 over a1 plus a2. Well, let's take the square root of both sides so we can try to solve for x. Now, this may initially look like a problem because we have the square root of a negative, but we can just multiply that negative through the fraction. So -1 times 5a3 minus a2, that's just a2 minus 5a3. So now what we need to determine is this ever possible? Could x be equal to plus or minus the square root of a2 minus 5a3 over a1 plus a2? Well, we know the only way that this would be false is if what's underneath this square root is always negative, because you can't take the square root of a negative number. But like we said, if we can find any solution where this is positive under the square root, then we will have proven linear dependence because we found one way that it's true without them all being equal to 0. Now, there are infinite solutions here, but we'll just show one. What if we let A3 and A1 both equal 0? Well, and this is equal to A1 over A1, which is just 1, and then we get plus or minus 1 as our solutions. So as long as A1 and A3 are equal to 0, and A2 is not equal to 0, because you can't divide by 0. So A1 equals 0, A3 equals 0, and A2 equals 1. Sure, A2 equals anything as long as it's not 0. Then this is a possible solution where not all of A1, A2, and A3 are equal to 0. And like I said, there are infinite solutions. This is just one of them. So we have proven that this set of functions here, y equals x squared minus 1, and y equals 5, is linearly dependent.